The world of electric current, resistance, and Ohm's law. This is what we've been building up to as we talk about electrons and the amount of charge they can carry per electron, and we talk about electric potential in volts. It's time to get into the world of those things doing some work for us in electrical devices. So we've talked about the correlations between gravitational potential energy and electric potential energy. And one of those correlations is to talk about a waterfall. If you harness the natural flow of water as it travels down, then you're able to harness power and actually create electricity. So they really are related. So we need this new concept. Current is the flow of electric charge. Now we've talked about the idea that it's the protons that stay put, and it's the electrons that move in an electrical conductor. So here's a case where we're going to talk about electrical current in amperes, in amps. So electric current will flow through. We really traveled back in time and found a Discman, and we have electric current flowing through our batteries into our CD mechanism, and we have moving charge and a conducting wire. Alright, so within a battery, a chemical reaction occurs that transfers electrons from one terminal to the other terminal. We call this maximum potential difference the electromotive force, EMF. That's in volts. So electric potential energy, electric potential, and EMF, and the voltage on a battery are all in volts, and they all represent the number of joules per coulomb of charge that is carried by that battery. So electric current is I, capital I, is the change in charge, coulombs, per the change in time, seconds. So that is 1 ampere. 1 coulomb per second is 1 amp of current, 1 ampere of current. So I is amps in A. That is electric current. There's two ways to do this. There's direct current. With direct current, the electrons travel one way through a resistor. We will say that they travel from the positive terminal of your battery to the negative terminal of the battery, even though that's not true. And that's the only direction they travel. Versus when I plug something into the wall, that is alternating current. What happens with alternating current is that the voltage changes from being a positive value to a negative value. And as the voltage travels up and down, the electrons that move in the circuit follow that. And so the electrons travel back and forth through an object. So a light bulb with electrons traveling back and forth will still light up. It just will kind of change in its intensity at a faster rate than we can pick up with our eyeballs, so it's not a big deal. Okay, so we're going to focus on direct current for our purposes here. The current in a 3-volt battery of a pocket calculator is 0.17 milliamps. 10 to the negative third amps. We have some really tiny numbers in a lot of this stuff that we're doing, so we have to be good with our metric prefixes, milli, micro. I think we're even going to get into nano, farads. So milli is 10 to the negative third, micro is 10 to the negative sixth, and nano is 10 to the negative ninth. In 1 hour of operation, how much charge flows through the circuit and how much energy does the battery deliver to the calculator? So 0.17 times 10 to the negative third amps. It's not good scientific notation, but it's accurate. 0.17 times 10 to the negative third. It's really quick. We don't have to set up some equation to make this equivalency. 0.17 times 10 to the negative third times 1 hour is 60 minutes times 60 seconds per minute, 3,600 seconds, would be 0.61 coulombs of charge. That's how much charge is running your calculator. And then if we want to talk about in terms of energy, how much energy is delivered, Well, the charge is 0.61 coulombs times 3 volts is 3 joules per coulomb. So coulombs will cancel and we'll be left with joules. 1.8 joules of energy is used to run your calculator for 1 hour. Pretty good. Now, we said quickly that when I put a battery in a circuit, I have a positive terminal and a negative terminal. And we say conventional current is that current will flow from the positive terminal of the battery through my device and then back into the negative terminal of the battery, where it will take the elevator from the bottom floor up to the top floor, have energy again, and then go around again. This is great analogy, except it's not entirely true, because it's the electrons that are moving, and the electrons are repelled from the negative terminal of the battery and are attracted to the positive terminal. It doesn't matter which way the electrons are flowing. It is a circuit. If the electrons don't have a path back to the other end of the battery, current doesn't flow. We have an open circuit, and electricity will not flow in that situation. That's what a light switch does, is it stops the flow of electrons. So in this case, it really doesn't matter which way they're flowing. It's just enough to know that there's a circuit and they can flow. All right, so this is a conventional light bulb, so it's not an LED. Most of our electronic devices these days will be LEDs. This is a conventional light bulb. A conventional light bulb is made with a metal tip at the bottom, then a ceramic insulated layer so that electricity won't cross paths, then a base that is metal that screws in, and then there's this wire that goes from the metal tip up through here and then out the side, that metal side. And this is a pathway for electrons to flow through this resistive wire. And when there's electrical resistance to the flow of electrons, that resistance reveals itself in heat and light. So what we want for our light bulb is for light to be generated. And so we'll flow electrons through there, and the flow of electrons will be resisted and we'll have light produced. So this is the other part. We're going to build up to Ohm's law. That's going to be huge for us. Ohm's law is the relationship between voltage, current, and then resistance in some electrical device. So here's our circuit. We're pretending that the current is flowing from the positive terminal of the battery through the resistor. This is the symbol in a circuit diagram for a resistor, this jagged line. Here's a switch, so that's the on-off switch. If we open the switch, then we don't have any current flowing. If we close the switch, we've turned it on, and current is allowed to flow. And current will flow from our batteries, both of them. Start with the bottom battery up through the top. If you stack two 1.5 volt batteries on top of each other, you have 3 volts of electric potential. Goes through the light bulb and then back down again. So that's our resistor. So Ohm's law then is this ratio to the voltage and current is constant. That is the resistance in ohms, the Greek letter capital omega. And so Ohm's law, as we see it and use it, is V equals IR. Voltage equals current times resistance. This is huge. There's all sorts of examples that we'll use with that. To the extent that a wire or an electrical device offers resistance to electrical flow, we call that a resistor. So the light bulb is a resistor. The other wires involved have very low resistance. We call those conductors, and we don't factor them into Ohm's law. We assume they have 0 resistance relative to our resistor in our circuit. So the filament in our light bulb is a resistor in the form of a thin piece of wire. The wire becomes hot enough to emit light because of current flowing through it. The flashlight uses 2 1.5 volt batteries to provide a current of 0.4 amps in the filament. Determine the resistance of the glowing filament. So two 1.5 volt batteries gives us 3 volts of electric potential divided by the current 0.4 amps, and we end up with a resistance of 7.5 ohms for this particular resistor. We can design different materials to have a range of resistances depending what we're looking for. There's a resistivity of different materials, so copper versus silver versus, I don't know, zinc or lead. They all have different amounts of resistance, and then if we design the device, we have the length, so resistance will increase the longer it is, and resistance will decrease as the area, the thickness of the device increases. What we'd like is to have lightweight wires made of relatively cheap material that have low resistance. So when we do that, we look at a bunch of different ideas, and okay, so the resistivity of copper is pretty low. We could get lower resistivity. Maybe if I jumped to silver, silver would be even lower resistivity. Unfortunately, silver is a little more expensive than copper, so we tend to use copper wires, sometimes metal alloys. What we would like to have is something that is really low resistance in order to conduct our electricity. It'd be something that's a really good conductor. Indeed, we'd love to have something that's a superconductor. We can get materials to be superconductors to conduct electricity without any loss of energy, but those only work so far as we have been able to design them at low temperatures. We have a superconducting magnet in the NMR in the chemistry department. That superconducting magnet has to be cooled. There's a jacket of liquid nitrogen around a jacket of liquid helium, which is really cold, and we need that kind of cold temperature in order for it to be superconducting. One of the great goals in physics and engineering and material science would be to design a room temperature superconductor. Then we could make wires out of that material, and devices wouldn't heat up. If you feel the bottom of your laptop computer at any point in time, you'll notice how hot it is. Mine is really hot right now. That is because there is heat being generated by the resistors and the electrical devices inside that instrument. That heat causes problems. Alright, so the instructions for an electric lawnmower suggest 20 gauge extension cord for distances up to 35 meters, but a thicker 16 gauge, kind of counterintuitive there, should be used for longer distances. And so we have some different examples here. Alright, resistance, I don't know if this is counterintuitive or not, will increase as the material gets hotter. So when you turn on the electric burner in your stove, the initial resistance will increase as the temperature goes up. Power then, so we have current in amps, voltage in volts, resistance in ohms. The other concept that we're used to with electricity is electric power. Power equals current times voltage. Remember, current is coulombs per second. Volts is joules per coulomb. So when we cancel out the units, we want a power equals joules per second. Just like it did in Physics 1 when you were running up the stairs and figuring out your power, joules per second, as you ran up the stairs. Electrical power in watts is the same joules per second. Now if we're using electrical devices with resistors, we can have a simplification here. Since V equals IR, we can plug in IR in place of V and say that power equals I squared R. Or we can plug in V over R in place of I and say power equals V squared over R. So there's electrical devices that use resistors. We can have other shortcuts for figuring out what the power consumed is. So power and energy consumed by our flashlight that we were talking about before. We have the current, we have the voltage. Now I guess we're going to go for 5.5 minutes of operation to figure out how much energy. So 5.5 minutes times 60 seconds per minute. So we wind up power equals IV, the current times the voltage. It's a 1.2 watt flashlight bulb, not very bright. And then the energy that's consumed in 5.5 minutes is 400 joules. 4 times 10 to the second joules of energy is consumed by that light bulb. Now this is different. Direct current is different from alternating current. I spoke of that briefly. This is stuff that we cover in Physics 3, so we'll set it aside for now, just enough to know that it exists. So we're trying to get past alternating current and back into DC current, and we're good because we're next going to talk about electrical devices in the next chapter. So we're a good start. We will get to more in the next chapter.